Hello and welcome back to our course on complex analysis. Today we will explore analytic functions and conformal mappings. So, our first goal is analytic functions. And in order to start exploring this concept, we needed to introduce the concept of continuous functions, and therefore limits of complex valued functions of a complex argument. So let's start the definitions. Okay, so we have a function f that maps complex numbers from our set omega into the extended complex plane. And it can be written like this: we have z from omega, that is a subset of the extended complex plane, and it is mapped by f onto omega from the extended complex plane. Okay, now that we have introduced the notation for our functions, we can write omega as its real part and its imaginary part. So, by rewriting omega and f of z as their real and imaginary parts, we can see that they indeed correspond to themselves, which is quite obvious, but it is also quite nice in my opinion. Now, let's define a limit of our function. So, we have a definition. So we have our set in the complex plane, we have a limit point of that set, and we have our function, and the complex number that will be the limit of our function. We will denote the limit of our function as such, and we define it if for all positive epsilons there exists a positive delta, such that for all complex numbers from our set so if that is in a delta neighborhood of that node, let's notice that the neighborhood is without the point itself. We introduced this notation earlier. Then f of z, so the point that z is mapped to by our function f will be in the neighborhood of a. So you can see that a neighborhood delta of our point Z0 is mapped onto a subset of the neighborhood epsilon of our point A. Okay, now that we have completed this, we can continue and speak about continuity of our functions. So we have another definition. So a function is continuous if its limit at a point is its value at that point, and it is extremely similar to the real limits of our real valued functions. And we can also define continuousness in a domain. So similarly to the real valued limits, f is continuous in a domain if it is continuous at every point of that domain, and we denote it as such. Okay, now we can write a little statement and continue to the more important topics. So, continuousness of a complex valued function of a complex argument is equivalent to continuousnesses of its real and imaginary parts as functions of two arguments, real valued arguments. And by using the properties of real valued limits, we can get the properties of complex valued ones. So if two functions are continuous, then their addition, subtraction, multiplication by constant, or multiplication of those two functions are also all continuous functions. And before continuing to defining the derivative of a complex valued function of a complex argument, I have a visualization for you. So here is a Desmos file, and the link, as always, will be in the description. So we have our axes, and we can move them. On the left axis, we will have our input, and on the right axis, we will have the output. So the values that the input is mapped to by our function f. Let's say that we have some point in our space. Let's see if the function, here we have z squared, is indeed continuous. So, do you remember? Here is a point, and the value that the point is mapped to. we have our epsilon neighborhood here, and we can move around that point. And indeed, for all epsilon neighborhoods, we can choose a delta. So we can move the epsilon and the delta, make them small, so that the mapped neighborhood of delta is a subset of the epsilon neighborhood of the output. And indeed, the function x squared is continuous. We can also look at the function like e to the x, for example, or rather e to the z. So we can move around our point. It would need to be closer to the negative values of real now. And here we can also choose the value of our epsilon and the value of our delta. As you can see, the mapped neighborhood is yet again a subset of the epsilon neighborhood. So e to the power of z is indeed continuous too. Now let's return to the value of z squared. And the next visualization will be shown when we will talk about the derivatives of our functions. Okay, now that we have looked at the limits of the functions, we can also define a derivative. So we have a definition. Okay, so for a domain in the complex plane, we define a derivative of function in the domain pretty much in the same way as real-valued derivatives. Okay, and please notice that we can have a different paths of our complex number z that go towards the z0. So we also need the derivative to exist for us to talk about it. And it, similarly to a multivariable calculus, it does not exist always. But we won't look at that options, and instead we say that the properties of our derivatives are the same due to the properties of limits, and calculation is pretty much also the same as real-valued derivatives. And after saying that, we can introduce the concept of differentiable functions. So first we have a statement. Okay, and now we define differentiable functions. Okay, we say that f is differentiable at a point if its behavior near that point at the neighborhood of that point is roughly linear. So we can see that we have the linear part and the small part, small non-linear. And we can also define a differential. So we define the differential, which you can think of as a portion of linear growth of our function at a point, similarly to real-valued one. And we also define small o notation, so we define g of delta z as a small o of delta z using the limit, which is also similar to real-valued ones. And we also say the equivalence of a function being a small o of delta z and its absolute value being a small o of the modulus of delta z. This can be easily proven using the limits. Okay, and now we have another statement that differentiability at a point is equivalent to the existence of the derivative. So, we have the equivalence here, and also we can see that A, by this property, is the same as the derivative of f, is it not? Okay, and now we have an extremely important theorem. I will also put it on a new page. It is this important. And in this theorem, we will introduce the Cauchy-Riemann equations. Okay. So, we take a domain in the complex numbers and the complex valued function. At this point, it is pretty much a familiar setup for us, and we express the equivalence of differentiability of f, so existence of its derivative, with the Cauchy-Riemann equations themselves. So, we say that And I forgot to mention that we denote that a function is a differentiable at a point or at a set. We denote such functions as members of the set of all differentiable functions at that point or at that set. And here we have the Cauchy-Riemann Equation theorem. We say that f is differentiable and that not if and only if, which is by the way x naught plus iy naught. If and only if the u and v functions are differentiable at that point, and the Cauchy-Riemann equations are satisfied, and we will derive them next. And please take notice, this is extremely important. While the continuous functions were pretty much equivalent to the continuousness of u and v, here the differentiability of complex valued functions is not at all equivalent to the differentiability of u and v, because we also need the Cauchy-Riemann equations to be satisfied. Okay. Now let us prove this theorem. So, the proof. Let's first prove, let's first derive the Cauchy-Riemann equations from the differentiability of our function. So, we say that f is differentiable, and this fact implies that there exists a derivative. And this is an equivalent notation of that one limit. Okay, and now we can do some substitutions. So, let delta z be equal to delta x. So it will go to the right. Okay, remember directional derivatives from multivariable calculus. This is pretty much the same. We can choose a direction of our derivative, and first we choose it as delta x. So it would be similar to partial derivative of x. And indeed, if we look at the u and v part, then we will have so it is equivalent to the first part of our Cauchy-Riemann equations. So partial derivatives at the point x comma y here. Okay, now we let delta z be equal to I delta y. So this time it will look up, thanks to the multiplication of I, and delta y, of course, we go up. Okay, and now we have the limit as delta y goes to 0, so I pretty much can copy everything. And please do not forget that delta z is equal to I delta y, so we also divide by I. Okay, and this is equal to almost the same thing, but divided by I. Okay, and 1 over I is equal to negative I. It is a very basic algebraic property. Okay, so we have negative I du by dy, plus here i's cancel out, so we have dv by dy. But since both of them are the derivatives, and the function is differentiable at that point, they are equal. So, by equating the real parts and imaginary parts, we indeed have the Cauchy-Riemann equations. But we still need to prove that u and v are differentiable. So let us have a look at the differential of f at point z0. Okay. Okay, we have proven the Cauchy-Riemann equations, and what we are left with is the task to prove that u and v are both differentiable functions of two real variables, arguments. Well, let us first look at the differentiable, or rather, delta f. Okay, delta f at the point z0. We can write it as its real part and imaginary part, so we would get delta u at x0 and y0 plus I delta v. Okay, and one more thing, we have already the condition that f is differentiable, so we can write it as f prime of z0 delta z plus little o of delta z. We can rewrite f prime as du by dx plus idv by dx. Okay, and now let's write its real part and imaginary part. Okay, we will separate real part and imaginary part, then we will set the real part equal to delta u and the imaginary part to delta v, and we will get something nice, hopefully. So, the real part is du by dx plus multiplied by dx, of course, minus dv by dx multiplied by di. And that is not it. I would also like to rewrite O of delta z, small o of delta z, as small o of the absolute value of delta z, plus I, small o of the, yet again, absolute value of delta z. Okay? This is by our equivalence that I showed earlier. Okay, plus I. Now, by using the Cauchy-Riemann equations, let me make a little cloud for them, I can rewrite here dv by dx as du by dy, and with the negative sign, and dy by dx as dv by dy. So let me rewrite everything. And notice that the absolute value of delta z is the same as the norm of vector x0 and y0. And I forgot the delta there. Okay, now by equating the real parts and imaginary parts, we get that delta u is equal to z and delta v is equal to z. So, the x naught is not selected. Okay, and please notice that this can be rewritten as delta u is equal to our matrix du by dx 0 0 du by dy multiplied by vector delta x delta y plus little o of the absolute value of a vector of z vector delta x delta y. And the same with delta v essentially. It was, I think these were called the Jacobi matrices. Okay, and as you can see, we indeed have for them their linear parts and the small o parts. So they are differentiable. Okay. Now let's prove it back that the differentiability in Cauchy-Riemann equations mean that the function is differentiable. We can say that we can yet again look at delta f. It yet again is delta u plus delta v by its real and imaginary parts. And now, since u and v are both differentiable, we can rewrite them both as, well, as the same. We can go through this process back. Okay? So, since both of them are differentiable, we get these values, and then by combining them back and using the CR equations, since they are assumed, we can back to this stuff, and we return to this one. So, hence f is differentiable. Which concludes our proof. Okay, and now let us have a look at some fascinating properties that I explored, and we can actually prove the Cauchy-Riemann equations using the chain rule. Well, of course it's not as rigorous as before, but it is simpler to think about, okay? By differentiating our whole function. So, let me take a new page, and we have f is equal to u plus iv, the same stuff, and f prime, if we look at a certain point, then we can differentiate everything by x. Here we simply get f prime of x plus iy. And when we differentiate by y, we get almost the same. But here we also multiply by I, because the derivative of this part by y is equal to I. Okay. And we get the same, but with dy. So, by setting those derivatives equal to each other, which they indeed are, we get what we needed. So, we get the Cauchy-Riemann equations. Okay, and now let us actually look at the other forms of our function f. And first I would like to look at the exponential or polar form of our function f. Like that. Now, when we differentiate by x, we get the same thing. So d by dx. Here is this yet again f prime simply. So when we differentiate r, nothing changes. When we differentiate by theta, differentiate theta, this r remains the same, but we also get I and theta prime from up there. Okay, now when we differentiate by y, it is essentially the same thing, but also we need to divide by I. And by setting them equal to one another, the multiplication by this cancels out because it is non-zero everywhere. And we get that yet again our real part and imaginary part are the same. So what we get is another form for the Cauchy-Riemann equations. And here dr by dx is equal to r multiplied by d theta by dy. And r d theta by dx is equal to negative dr by dy. Or I like to take r to the same side, so we have that d theta by dy is equal to 1 over r dr by dx, and d theta by dx is equal to negative 1 over r dr by dy. Okay, now let's assume that the function has algebraic form, but the argument has polar form. So we have f of e to the I theta Okay, this is a little fascinating. Now when we take the derivative by r, so only e to the I theta goes down in the left side, and on the right side we have the same stuff. When we differentiate by theta, on the other hand, on the left side we get r times e to the I theta, and yet again another I. So we get r times I e to the I theta. And everything else is the same. And yet again, by cancelling everything out and equating the real part and the imaginary part, we get another form of the Cauchy-Riemann equations. And here, du by d theta. Or let's start with du by dr. It is equal to 1 over r times dv by d theta. And du by d theta is equal to negative r dv by dr. So you can see that the derivatives by theta are divided by r, or the other way around, whatever. Now we have the last one, and we assume that both the function and the argument are in their polar form. So when we differentiate everything by r, on the left side we get simply the e to the theta part, and on the right side we get everything that was taken before when we had the algebraic argument. And we get the same stuff here, and when we equate the real and imaginary part of the cancelling out the exponential, we will get another system. Okay, so now we can have a table of our various forms of the Cauchy-Riemann equations. Oh, okay, here in the top we will have the argument, or rather the input. And to the left side we will have the function. So we will have either algebraic or a polar. Okay, so we end up with this table. Now let's proceed with defining analytical functions. So f is analytical in a domain if it is differentiable at every point in that domain. And we have a notation for it. It is a wiggly A of omega. And f is analytical at a point, we also can define z. If there exists a neighborhood of that point, that f is analytical in. And my apologies, I messed up the notation here. We have analytic functions, not analytical. Okay, and we also can define that f can be analytic at infinity. Okay, so f is analytic at infinity if f of 1 over z is analytic at 0. And just like that, we have talked about the analytic functions and the Cauchy-Riemann equations. Now we will look at some properties of those functions, and we will also talk about conformal mappings. And of course, we will explain the hydromechanical and geometrical meanings of the derivatives here, so stay put. Okay, now we have defined the complex functions of a complex argument. We have defined continuous functions, differentiable and analytic functions. And now we move on to define the conformal mappings. Okay, so we have a general setup here. We have our function, a domain, and a curve, a Jordan curve in particular. And the curve starts with the value of that node. Okay, and now first we need to define the coefficient of stretch of our function. So we have a local linear stretching factor. It is written as k sub f of gamma and z naught, and it is defined as a limit of the absolute value of our derivative. So it is so you can see that it is the limit of the quotient of the distance between 2 points on the z-plane and 2 points of the omega plane that those z-points are mapped onto. So it shows by how much the size increases after the mapping of f. Okay, so if the limit exists, of course, because it doesn't always exist. So if it is non-zero and it does not depend on the curve, and both on the shape of the curve and on the parameterization, then f is called a mapping of constant linear stretching factor at our point z0. And now we can define the conformal mapping. So it is conformal at a point if its derivative at that point is non-zero. And we also define the conformality in a domain if it is non-zero at every point in the domain, of course. Okay, so we have defined the conformality in a domain too. But before we continue, I'd like to mention something. And I kind of forgot about some stuff and made some mistakes. First of all, it is supposed to be du by dy here. And the second thing is back there I wrote matrices, and they are supposed to be collectors. Just like that. Okay. And now we can return to our conformal mappings. And we continue. We have a little lemma here first. Yeah, and I forgot we actually don't need to say factor here. Just a function of a constant linear stretch. It is quite clear because the derivative is non-zero, it exists, and hence its absolute value exists, and then the limit also exists. It is quite straightforward, and as we can see, that the coefficient is the value of the derivative. And allow me to draw a little diagram of this. So we have our Argon diagram. We have a circle in its center. It is a neighborhood of the point z0 with the radius delta z, and we have our point z on the circle there. Now, what is it mapped onto? By a function f, and of course f is conformal at z0. As the point is mapped onto a point omega naught. And the circle is mapped onto a circle-like shape. And the distance from omega naught to omega is defined as the absolute value of f prime of z naught. multiplied by the absolute value of delta z. And as you can see, it will approach the circle. And in particular, let's look at delta omega and its absolute value. So we have, by definition of our derivatives and differentiable functions, we have this result here with little o, and of course as z approaches z0, so delta z approaches 0, it will approach the absolute value of f prime of z0 multiplied by the absolute value of delta z. Okay, and as you can see, the accuracy of our stretching is little o of delta z. And I'd like to add another little note here. The value of our Jacobian of u and v at point x0 and y0 is of course the determinant of the Cartesian here. And it in itself is equal to our Laplace operator. Or rather, to this value, by the Cauchy-Riemann equations. And it is the absolute value of our derivative squared. And it is strictly greater than 0 at our point. And now I'd like to have another statement here. So the image of a domain is domain 2 of a conformal mapping. And this statement we shall not prove because we will return to this statement in the future in the last chapter of our course on more difficult topology. Okay, now that we have looked at the geometrical meaning of the absolute value of z, so it is the coefficient of linear stretching, right? The vector. Now we will have a look at the geometrical meaning of the argument of our derivative. Okay, so let us have a conformal function in a domain. Let's first have a little reminder of the meaning of the derivative of a complex valued function of a real argument, so of a curve in the complex plane. Okay, so as the derivative at a certain point is the tangent vector to the curve at that point, and the argument of the tangent vector is the angle between it and the positive real line. Okay, and now we have remembered what the angle of the derivative, the argument of the derivative, means geometrically. Now let us expand this knowledge, rigorously of course, onto the complex valued functions of a complex argument, of a complex variable. Let us have a curve, gamma of t, and map this curve onto another curve, gamma wiggly line of t. Okay. Of course it is from A and B here, and let us look at the derivative of our new curve at a certain point. For example, let's take A here. And now we all would like to look at the argument of the derivative of our function. So we take the argument of the mapped curve. Of course we have the principal argument here. And that not, of course, is the value of gamma at A. And now we can use... I forgot to write the argument. And geometrically it is indeed correct. We do not go out of bounds. And now we can rewrite it so that we can get the value of the argument of the derivative of f. So what is it? And let me draw a diagram that explains it further. Okay, and let's look at what our curve and its tangent vector are mapped onto by our function f. Let's say that the point z0 maps onto the point omega naught. This is the tangent vector to our new curve at the point A, and we look at its argument. Okay, so the argument of the derivative is the difference of arguments of our mapped curve and initial curve. So it says to us by how much the curve rotates at a certain point. But a very fancy thing happens when we consider another Jordan curve. So we get another curve, and t is yet again from A and B, from the interval. Now let's generally the equation here is the same. Now consider the angle between the two curves at this point. I will denote the angle as such. Okay, so by subtracting, we get that it is the difference of the angles. Okay? And if we substitute the values of arguments of our weekly line curves, our curves that the initial ones are mapped onto, then the argument of f prime at the point z0 cancels out, and we indeed get the same thing, but without the weekly lines. And this gives us a very important fact about conformal mappings. It is the fact that they preserve angles between the curves, and of course not essentially between the curves, but essentially between anything. So the conformal mappings preserve angles. Now, when is a function conformal? When its derivative exists and is non-zero at every point in the domain, it is so cool, right? Yes, but in fact, we can we can go the other way around, and in fact, the if f is a function of constant linear stretching and it preserves angles, then indeed it will be a conformal mapping. So the derivative definition and the stretching and angle preservation definition are equivalent. And now we will prove it. So we have a theorem. Okay, so it states, as I have already mentioned, that f is conformal if and only if u and v are differentiable in the domain omega, and f is the mapping of constant linear station and angle preservation. Okay. So, the first condition is that the set of u and v is a subset of the set of all differentiable functions on the domain omega. And the second condition is the one that I have mentioned twice already. So the forward proof we have already shown. We have already shown that conformal mappings possess those properties. Now let's show that it is also true the other way around. Since u and v are both differentiable and u plus iv is a mapping of constant linear station, we can show that u plus iv satisfies the Cauchy-Riemann equations. So let's show that. Okay, now consider two orthogonal lines that are curves essentially, and what they are mapped onto. Since f has the property of angle preservation, this angle will in fact be a right angle too. So let me draw it in a better way. Okay, something like this. And this mapped vectors will be the tangent lines. So it will be u by y and v by y, and u by x and v by x, since the two lines are parallel to our axis. Okay, and now we can rewrite a bunch of facts using the property of angle preservation. Since they are orthogonal, if we exchange the places of coordinates and multiply one of them by -1, then we will get parallel vectors. Now, let us look at whether they are parallel or inversely directed. Since they are parallel, we can look at their dot product, so let's do that. This is the determinant of the Jacobian matrix. So it is the Jacobian of A and V. And here it is non-zero. So they are indeed parallel. Okay. Now, but you may say, it doesn't prove anything. The Cauchy-Riemann equations may in fact still be the opposite side. And I will agree with you. Now, from the property of constant linear stretching, the length of these new vectors here, they are the same. And since we just exchanged the places of our coordinates and multiplied by -1, the length of this one, orthogonal one, is still the same. Hence we get the Cauchy-Riemann equations, either positive or negative yet again. By negative Cauchy-Riemann equations, I mean the ones that we know, but one side of the equations is multiplied by -1. Now, let's assume and go from the contradiction that negative Cauchy-Riemann equations is true. So, we get a contradiction that 0 is less than 0, and hence the Cauchy-Riemann equations are true, and f is analytic in omega. And since the Jacobian is greater than 0, the absolute value of f prime is greater than 0 too. Hence f is conformal. So let's write it down. Okay, so f is conformal, which is the fact that we needed to prove. And if you are questioning why the Jacobian is greater than 0, then it is by the constant coefficient of linear stretching. They can only be stretched in one way. Okay. Let's look at conformality at infinity. So, let the value of f at infinity not be equal to infinity. It is similar to differentiability. We just take the argument of 1 over z and make it conformal at 0. And it implies that f at infinity is conformal too, by definition. Okay. Now, what happens if f is equal to infinity at some point? Here we use a similar technique. We just take 1 over f, which is equal to 0 at that point, and we see if it is conformal. And similarly, if f at infinity is equal to infinity. Okay. Now we have a definition. In the real analysis, we have a concept of injective functions. So, for any two arguments, we have different values of the function. Here, we have a similar concept, but it is called univalent. So, f is univalent in omega if for any two arguments the values of the function at them is not the same. And now I would like to state the Riemann theorem. We will prove it at the end of the course, and it is just incredible. So, there exists a unique, univalent, and conformal mapping from omega to g that maps that knot onto omega knot, and the argument of its derivative at that point is alpha. Okay, now I have a visualization, and then we will talk about another interpretation of analytic functions. So stay tuned. In the previous visualization, we have talked about how continuous functions, complex valued, map our neighborhood to subsets of other neighborhoods. Okay, and now I would like to talk to you about conformal mappings. So, we have a delta neighborhood here. And we have a curve. And together with the delta neighborhood, the curve is also mapped onto the green curve here. Okay, and here I have the original blue curve and the mapped green curve. And it's not very visible here, but of course the derivative will approach the angle between these two curves. Here we have the error because we're not seeing it as a limit. Okay, and also I have the visualization for the linear stretching factor. We can see the green curve here, and the ends, the length from the starting point to the end point. And it will approach the absolute value of our derivative at that point, multiplied by the original distance from the starting point to the end point of the blue curve. And as always, you can change the function. You can make it anything really, a linear function, a cubic, here it is. Of course, you have to be careful so the values don't go out of bounds. We can also have the exponential one. It is also quite neat. And you can explore. Of course, as always, the link will be in the description. Feel free to explore those different functions, different delta values, etc. And hopefully, this visualization has been useful for you to clearly understand the geometrical meanings of the argument of our derivative and the absolute value of our derivative of conformal mappings, because everything breaks down if the value of the derivative is equal to 0. Okay, hopefully you liked this visualization, and let's continue to the final topic of today, which is hydromechanical interpretation of analytic functions. Okay, so the next topic is the hydromechanical interpretation of analytic functions. And let us have an analytic function. Let me describe it. It is f of z, of course. U and v are continuously twice differentiable in omega, and f is analytic in omega. Then, as we have already defined and talked about it, the pair u and v, this one here, is a pair of harmonic conjugate functions. Okay, now we define a plane parallel vector field. So a vector field is parallel to a plane. In our case, it will be parallel to the xy plane. Okay, and it will have xy as inputs. So we consider it. Okay, so the first coordinate is the derivative of u by x, the second one is the derivative of u by y, and the third one is 0. And of course we have x and y as our arguments. Okay, and now consider the potential of V. And it is easy to understand that U is the potential of V, of course vector V. In other words, V is the gradient of U. And of course we may use our favorite noble notation. And now let's look at the divergence of V. And as always, the divergence of a field that has a potential, it is zero, and hence V is called solenoidal. Now we consider the curl of V. Okay, it is calculated as this determinant, and if we expand this, then for the first two coordinates we get 0. And for the third coordinate we get this by calculating the determinant. And using the fact that they are the harmonic conjugate functions, this then also cancels out to 0 by the Cauchy-Riemann equations. So it is 0 vector. In omega, of course. Here we need to make a conclusion, and the conclusion is that every analytic function corresponds to a solenoidal and conservative vector field. The real part of f, so our u, is the potential of the field, and hence, if we remember, you can determine f, given its real part, with accuracy to an additive constant. And hence, we can also give a name to our f. F is called a complex potential of the vector field. So if its real part is the field's potential. Now, can we get back, given the field, can we retrieve our u and our f, of course? Let us have such a field. And let it have a form where we do not know the first two coordinates, they are some functions, and the third coordinate is 0. And of course they are continuously differentiable. And another one fact that we need to assume is that the value of v is not equal to 0 in omega. And now, consider the curl of v, and when is it equal to 0, given our shape of the vector field. only when this determinant is equal to 0, and this, by expanding, happens if and only if the partial derivatives of v1 and v2 by y and x respectively are equal. In omega. Okay. Hence we can have a differential. We consider such a differential, and given the fact that their partial derivatives are equal, this differential is exact in omega. Which implies that there exists a function that is twice continuously differentiable in omega, such that a small omega, let's call it omega 1, since that omega 1 is the differential of u. So, and the partial derivatives of u are equal to our functions phi1 and phi2. And hence, u is the potential of our vector field. Now let's see which factor goes from our divergence, which is also supposed to be equal to 0. We get this one condition, and hence we can consider another differential that will also turn out to be exact. Of course, it is exact in our domain omega, and it implies in the same way the existence, and here we call the function v. Okay, and if we look a little bit upper, so here, and here, then we can see quite clearly that u and v satisfy the Cauchy-Riemann equations, and hence f is analytic in omega. Hence we found a one-to-one correspondence of such an analytic function and the vector field v. And of course, don't forget that we can add plus c to our f, and the correspondence will be the same. Now, how do we interpret v? Because we have already said that u is the potential of our field. Consider V is not equal to constant on all the pairs of x and y, but we consider this as an equation of x and y. Okay, now what do we get? How could we consider the derivative of y by x? We could rewrite it using our v. Now, why do we have a minus sign here? Since we consider the x and y along which v is constant, then the partial derivatives, but in particular the differential of v along these numbers is 0. And after some differential algebra, we get this. Okay, and then we get the negative sign. Okay, and of course it is 5/2 divided by 5/1. Hence, if we look at a vector that will be tangent to our curves, I suppose that those are curves. This is an equation of the tangent vector if its x component is equal to 1. And by writing it in phi, we get this. And this vector is parallel to phi1, phi2, and 0. And this is called a streamline of V. And what does it mean? It is basically a path that is always parallel to the speed of V. So you can see it as a solution to a differential equation. It basically, I will show it to you, of course, in a visualization. I have one more. But basically, if we let a particle go with a vector field, so that the vector field describes its velocity, then the path will follow a line that is exactly v of x and y is equal to constant. It will describe that line. Okay, now to make it more accessible and simpler, let's have a look at the visualization. Okay, and this is the final visualization for today. We will visualize the vector field that our complex valued function generates. Here I have a condition for the analyticity of our function. So we will see if it is analytic. You could show those, and if it is equal to 0, then it is analytic. Here I have the components. I visualize the field, and it is very fascinating. Here we have the properties, so we check that they are true for our field. And as you can see, they indeed are equal to 0. And now we have the visualization of our path. So the white lines here, as you can see, they are the path of constant speed, where the speed is equal to v, and they follow the particles. So, if you put a particle near the center, then it will follow line over that one. For example, a particle here, it will go over there, along with that line. Okay. And now, let's explore several different functions. Let's look, of course, I haven't mentioned it yet. The blue, in this case, the cyan, I think the color is named. Colors mean that we have slow progression, and the yellow ones mean that we have a quick progression. So the speed is slow versus quick. If you look at the parabola, it looks like that. We like to go into the corners. If we look at z to the power of 10, for example, this is the linear one, and this is z to the power of 10. As you can see, it looks like a spider web. That is very beautiful, in my opinion. Let's make it a little bit higher. Okay. If we look at the constant, that of course we won't have any movement at all. As I have already mentioned, the linear looks like that. You just go to the right along a line. We can also look at the exponential function, and it will look like that. So we can see that the speed is generally slow, and it rapidly increases to the right, in the right side. If we divide that in the exponent, then the speed will be increasing a lot slower. So we can see that the hue changes more gradually. And in general, you could explore functions as you wish. For example, let's say that we have e to the power of negative z squared. This is e to the power of negative z. And let's wait until it computes the square. It becomes very messed up. Okay, we might wanna move in for a little bit. Yeah, a little problem is that you can't easily change the scale. So we might get artifacts like that, but near zero, it works pretty well. And as you can see, the lines are like that. Okay. The color also got a lot messed up here. Well, that is because that grows quickly, and e to the power negative z, especially along the imaginary axis, grows very quickly. Okay, what might we want to test next? We might test something like a non-analytic function and see what happens here. So let's take the absolute value of that, and it looks like that. As you can see, it also is messed up, very messed up, because the absolute value of that is not analytic. We might look at the reciprocal of that. As you can see, it is also quite nice here, even though the colors do struggle to show, because near zero it will grow very quickly. And the same goes for 1 over z squared. It is very nice in my opinion. So feel free to explore this graph, and I will also leave the link in the description as always. So thank you for your attention. Thank you for staying with me this long. Hopefully it was informative video and you got to learn something new. Feel free to explore with the Desmos graphs in the description, and thank you. Bye!